Hi, your friendly neighborhood Marica here. This video should be useful in informing you about the monomers ethylene, ethene, and vinyl chloride, as well as the polymers polyethylene, polyethene, and polyvinyl chloride. I've also added a few additional but handy explanations, as well as some uses and applications of the polymers discussed. It is important to understand that polymers are long carbon chains that are made up of thousands of monomers. I am fully aware that there are people in the audience that don't speak Greek, so allow me to translate. Polou is the Greek word for many, whilst meros is defined as a share. When these two were added together originally, it became polymeros, meaning having many parts. Polymeros eventually became the word polymer as we know it today.
The word monomer consists of the two Greek words monos and meros. Monos, when translated, means alone. Hence, monomer carries the definition of one unit. Since atoms are all very small particles that would be very difficult to use in this demonstration, I will rather be using marshmallows and toothpicks to represent the atoms and the intermolecular bonds present. The white marshmallow is going to represent carbon, whilst the blue marshmallow represents hydrogen, and finally the green marshmallow will represent chlorine.
Unfortunately, my marshmallows don't show that chlorine is actually a whole lot bigger than hydrogen is. For now, it's not really a bother, but it will come back to haunt us. Now that we know what monomer means, allow me to introduce you to one. This is ethylene. He has the nickname ethene. He has two carbons joined together by a double bond, and in turn each carbon has two hydrogens that belong to them, and only them. Think of a bad rumor that will cause the bond between two friends to break. Similarly, a polymerization catalyst will cause one of the bonds between the carbons to break. This step is known as initiation. After the bond has been broken, each carbon now has a free electron that wants to react with other atoms or molecules, and in this case that would be other broken ethylene molecules. This step is known as propagation. It explains how one broken ethylene will react with another broken ethylene, and another, and so on, until you eventually have thousands of ethylene molecules forming part of what is now known as the polyethylene chain, which is written as the broken ethylene in brackets times n, where n is the amount of times that it repeats. Upon removing the polymerization catalyst, the last step is initiated, termination. This will cause the whole ethylene monomers to remain whole, while the readily existing polyethylene bonds with another molecule or atom to close off the chain. Even though the molecule on the ends of the chain may not be ethylene molecules, it does not affect the polyethylene as a whole, because the end molecules are insignificantly small in regards to the rest of the chain. It is important to note that polyethylene and polyethene is the same compound, just as ethene and ethylene are the same molecules. LDPE is a low-density polyethylene. This means that it is flexible and described as amorphous. LDPE is majorly used in the making of film, but is also used in extrusion coating, injection molding, wires and cables, and other day-to-day objects. HDPE is a high-density polyethylene. This means that it is extremely rigid and is described as crystalline. HDPE is majorly used in blow molding, but is also used for injection molding, the making of more rigid film, pipes, and other more rigid or hardcore objects. HDPE is obtained when a free radical initiator, FRI, is used to initiate the polymerization of ethylene. One of the downsides to this model is that it only represents a basic polyethylene chain and does not show when and where potential branches will occur, as in the case of LDPE. This model does allow for bonds or electrons, represented through the toothpicks, to be moved around. However, doing so is a rather tedious task. To avoid this, I ended up using multiple different models to represent the different stages of the polymerization process. Even though the rigidness found within HDPE is not shown in the model, the flexibility of the LDPE is shown, since the model chain can be twisted and bent to a certain extent. Considering that the use of a free radical initiator, FRI, during polymerization of ethylene will cause LDPE to form, and that the use of a polymerization catalyst, PC, will form HDPE, it is safe to assume that there is a difference between an FRI and a PC, which there is. The biggest difference between FRIs and PCs would be that a PC merely lowers the reaction rate and hence activates the polymerization process, but does not physically or chemically partake in the reaction. On the other hand, FRIs bond to a monomer to create another, larger free radical. This reaction will continue to happen until two free radicals come together and form bonds to terminate the free radicals. I've already introduced you to one monomer, but I'd like to introduce you to a second monomer, vinyl chloride. He doesn't have any nicknames. He also has two carbons joined together by a double bond. However, he likes to accessorize. This means that only one of his carbons has two hydrogens attached to it, because the other carbon has one hydrogen and is bedazzled by one chlorine. Just like ethylene had to go through this three-step polymerization process to become a polymer, so does vinyl chloride have to go through that exact same process to become polyvinyl chloride, or PVC. This polymerization process can be activated either through the use of a PC or an FRI. Just a quick recap of the three steps in the polymerization process. Initiation. The FRI or PC breaks the double bond that is situated between the two carbons. Propagation. Thousands of monomers come together to form the polymer chain, PVC. Termination. The PC is removed, or two FRIs react to form a stable molecule and hence stop the polymerization process. It is important to take into account that the atoms or molecules at the end of this polymer chain are insignificantly small and do not affect the overall structure or properties of the polymer. Since PVC is naturally extremely rigid, its initial uses were limited commercially. However, after the discovery of plasticized PVC, a flexible and inert product, polymers became popular in the commercial world. PVC is majorly used in pipes and window frames, but is also used in flooring, cables and wires, films, plastisols, coatings, hoses, flexible sheets, and other rigid and flexible items. The use of different colors to represent hydrogen and chlorine is only effective when dealing with people that do not suffer from achromatopia, or color blindness. In reality, the chlorine atom is significantly bigger than the hydrogen atom, which this model fails to represent. It is important to note that the size of the atoms matter, since the decrease in negative space is what causes PVC's rigid qualities. At least this model is successful in representing the polymerization process of vinyl chloride molecules. I want to go back to why PVC is so rigid. When looking at the polyethylene molecules, it is observed that a lot of negative space is available for the chain to twist and bend in. However, the increase in atom radius from a hydrogen to a chlorine causes a decrease in negative space from the polyethylene to the PVC. This decrease limits the available space in which the molecules can bend and twist, hence causing it to be rigid. And that's the end of that. I really hope this video was informative, unboring, and scores great. So shout out to Mr. Lucas and Ms. Wilkins for patiently sitting through this video because they have to. And lastly, I want to say thanks to my two great friends, Bez and Bez, for helping me make a video out of my research. You guys are the best.
Yeah, I like the little emphasis on my name.